You guys picked a great day to come up, great weekend. We put our order in a long time ago for clear skies, and it finally came through. So we're going to have a great opportunity to enjoy some outstanding presentations, as well as night sky viewing. And tomorrow we'll have another full day's worth of programming, solar viewing, and again, more presentations and workshops. So we have a lot to actually get through today, so I am actually going to withhold or refrain from my standard intro, and I'm going to introduce our first speaker, which is George Normandin. He is the president of the Kopernik Astronomical Society. That's the astronomy club that is resident here, and he's going to, we call this George's Best Images. And so, George, if you want to come on up, and we'll let you, yeah, so just, you will be in a second. All right. You will be in a second. Give me some more audio. Go ahead.
On?
There you go.
I guess I'm on.
You're on.
Okay, as Drew said, I'm George Normandin. I'm from the KAS. We certainly invite anybody here to come and join us. Why should we have all the fun? We're an astronomy club associated with the observatory, and we're also the sponsors of AstroFest. And I just thought I would cover what is AstroFest. If you're looking to buy a telescope, you should be down at Walmart. Well, actually, we're selling them here too. And back in the 1970s, they started a worldwide program called Astronomy Day, which went to Astronomy Week and Astronomy Month. It's basically a celebration of astronomy. And places like Kopernik and museums and colleges, astronomy clubs would hold Astronomy Day as a way of celebrating and giving back to the community and getting people interested in astronomy. So that's basically what we're here for. However, we found back in the old days that it was always cloudy when Astronomy Day was supposed to happen in the springtime. So we switched to the fall, and you can see we have these wonderful clear skies. And we renamed it from Astronomy Day to AstroFest. So that's basically what we have. And this is a low-key sort of presentation here. We're just going to enjoy some images that I've taken with some of the latest with some of the telescopes here mostly, but also my own scope at various locations. So I've gotten that particular view of the Milky Way wide field view is from where I hang out a lot up in the Adirondacks, Indian Lake, but also at Tupper Lake. And Cherry Springs International Dark Sky Park in Pennsylvania. Anybody interested in seeing really dark skies, talk to me later, or just Google Cherry Springs. And of course, Kopernik Observatory. And that pretty much covers where my images are coming from. Okay, me a long time ago with the Optical Guidance Systems 20-inch Retro Creighton, that's an F8 for you telescope geeks. I helped install this thing back in 1993, so it's been around a long time. And we started with film, and we went through a couple of iterations of CCD cameras, and you'll see some of the images on here I've taken with digital DSLRs, like I use Canon, but basically commercial telescopes in addition to the current professional FLI. Okay, this is, I mentioned Cherry Springs. This is me. I guess I had a big breakfast. I used to weigh more. At Cherry Springs in 2018. And when I mention a 5-inch white telescope, that's my scope on the Losmandy mount there, and a CCD camera attached to it, and I'm running it with a laptop on that little table. And that's what you get at Cherry Springs, except it's super dark there. So when I mention that scope, that's it. Okay, here's me at the Stellafane Telescope Makers Convention in Vermont, and you see the same white scope on the left, and at least some people in here recognize that big Dobsonian in the background because it's theirs, and my old Dobsonian in the front. And the Dobsonians you can't image with for the most part, and they're mostly visual scopes. And for the last 3 years at least, I've been concentrating on mostly visual stuff. So some of these images are a little bit on the old side, but we're working on getting our 20-inch working here, and I want to get back into imaging. Well, this is what happens when you point your camera at the North Star and just leave it open and let it record. And that's proof the Earth rotates, because it's pointed right at, that star there is Polaris, a little bit off the pole. The pole is in the center. And you can see you got blue stars and red stars, white stars. The color tells you the temperature of the star for 99% of stars. So that's a color temperature thing and a proof that the stars rotate. And you could do that in your backyard, put your DSLR or other camera on a tripod and open it up and let it trail. We started here at Kopernik way back, the last of the film era, with Comet Hale-Bopp back in the old days. And I forget what that was taken with, but probably an old 8-inch Schmidt camera and film. But that was pretty much the end of the film days, although we were already into digital. At one point, we had one of the first digital cameras sold, the old SBIG ST6, which was one of the first digital telescopes available to amateur astronomers. Okay, this is just like random stuff. A lunar eclipse from September 27th, 2015, taken up at Indian Lake in the Adirondacks, and a few more images further out. Another picture of it, a wide field, like a 24mm lens. This was it with a DSLR. I had a hard time that night because my landlord sent all the people in his 8-unit motel down to look, and I made the mistake of giving them my binoculars, and I had to fight for 2 hours to get the binoculars back, especially when it got really dark and they could see the Milky Way and all the stuff in it. Here's an old film image, way back in 2004, an old film image through the 20-inch, Kopernik 20-inch, of another lunar eclipse, October 27th, 2004. The Cocoon Nebula and in H alpha. We have special filters that are designed to let one narrow band color through. They're very narrow band. They throw away 98% of the light, and they let one color through. Hydrogen alpha is the first spectral line from hydrogen. When hydrogen nucleus, which is a single proton, captures an electron, becomes an atom, it sends out a photon in this one particular color. It's a deep red. It's hard to see, but you can see it. Deep red, but we often just image it in black and white. That's what H alpha is. And you're going to hear me talk about that often. If any of this, you have questions about it or any of the objects here, come and ask me after the program or later today or tomorrow. That's that nebula in H alpha, and if it was in color, it would all be a very deep red. And what is that? Remember, I said the gas is actually emitting that deep red color, so it's sending out light. It's a light source, like a light bulb, like a neon tube. And the star in the center is a very young star, and it's producing lots of hydrogen alpha, or lots of ultraviolet light, and it makes that gas glow. And the dark patches in there are not where there's no nebula, it's where there's dark, cold gas and dust between us and the nebula. So it's kind of hiding it. And you'll see this looks like there's missing stars in some of these spots. That's areas where, again, there's dark gas and dust between us and the object that are blocking it. Here's another telescope that I got a lot of pictures through over the years, the 6-inch f12 astrophysics refractor out in the observatory. It's one of 25 ever made, and beyond that, it has the 3 elements in the lens. 2 of them were made in 1987, and the one in the middle was made in 2023 when we sent it back for repairs and they broke the center element. So we have the only astrophysics in the world that was made over a vast, long period of time. It's a fabulous solar, lunar, planetary telescope and can be used for deep sky also. And here's my friend Art, who you all know, who's trying to adjust the counterweights on it. And as you can see, it's a very long, heavy telescope. We also, here's some old-time aurora. This is film also. That goes way back 2010, aurora here. And here's my buddy Patrick, who's floating around somewhere, who's playing around with, in this photo, with our C14 Edge HD, which is a telescope that can be used for just about anything, jack of all trades. It's optimized for imaging, although we use it mostly for visual, but we can do imaging with it since it's specialized for that. I don't have any images through that. Hopefully I will in the future. Here's a drone view of Kopernik, and you'll notice here's the observatory, and you can see how it sits on top of a hill, which is an advantage. And when the river valley gets all fogged over like that, which hopefully it will tonight, it holds in all the light pollution and the light, and it gets much darker here than it normally is. So that's an example of, this is a very good site for doing astronomy. It's not world class, but it's better than 95% of most organizations have. Another image of Kopernik, and this is back before we painted the domes, should update this to a prettier picture. Some of the latest, but again, before we painted the dome. This is one of our Dobsonians. I don't know whether we'll bring it out tonight. You can only look through it, but notice the eyepiece is on the side. So as the telescope moves around the sky, the eyepiece stays in the same place. And that means that people in wheelchairs can use this telescope. No pictures out of it, though. That's the guy who built it, Brian Goodson, the owner of New Moon Telescopes. And that's Patrick there, who is helping him set it up the first day he brought it up. Here's our 20-inch with the current FLI camera system, Finger Lakes instrumentation, which is made in that exotic Asian city of Binghamton, New York, and Rochester. But that's what we have on there. Now you can't look through the telescope because it's too hard to take this camera off in the back. Notice this little 80 millimeter. That's a very fine telescope of it on its own and can wide field image a lot. Another picture, you can see the FLI camera system in there. We'll tell you about it out in the dome. And that's the 80 millimeter, which you can look through or you can image through. Is a very fine telescope. A close-up of the camera system. It's a black and white camera chip, so to take color images, we have a wheel in here with filters that rotates around. A little motor rotates it around, and you take an image in each color. We actually have 7 filters in there in each color, and you put that together to make color images. And that's part of the control software and so on. That's where we get our golden eyepieces over here, the bucket of gold. Here's some of our staff looking for bugs in Pennsylvania. No, you point them up to look for them. These people have never been here, but I thought I looked cool, so I put them in the presentation. Another look at Kopernik. Okay, here's just a DSLR on a tripod down at Cherry Springs Dark Sky Park in the springtime, and you can see the constellation of Leo, the M44 cluster, which you can see naked eye, and of course Mars was up near Leo at the time. So that's the kind of thing you can do. Now you can do that type of imaging with a cell phone. Supernova remnant. Star exploded in, 1054, I believe, in the constellation of Taurus. It was so bright that it was brighter than the full moon. You could see it during the daytime. You could see it for about 9 months. It's when it appeared and how it changed in brightness and color was recorded throughout Asia, in China, Japan, Korea. But what you didn't have was nobody noticed it in Europe. It was either cloudy for an entire year in Europe, or people knew in 1054 to keep your mouth shut because they'd burn you at the stake if you said you'd seen a new star in the sky. So it was not a wise thing in medieval times in Europe to look at it. Let me see. I want to go back and look at that again. This is the bluish stuff is just high energy electrons near the speed of light, and they go through the magnetic field that's being created in this thing, and as they spiral down the field lines, they give this blue light off. The red light is again H alpha, glowing H alpha, tremendous explosion, millions of times brighter than our sun. About 1 out of 100 stars will do this when it reaches the end of life. Okay, star cluster in M3 in Canes Venatici. I was just looking at this 2 weeks ago down at Cherry Springs visually. Here's a picture of it through my white 5-inch refractor, and I think this is a DSLR that was on there. This is the same star cluster through our 20-inch with the current camera on it, current camera system. At least 500,000 stars, and is very impressive when viewed visually through a larger telescope. Back before we had the current camera system on, we had an earlier one, and it went on and off, and we could add a lens that would cut the telescope from f8 down to f5, which gives you a wider field of view. So that's what that is, wider field of view, older camera. Okay, M5, same thing. Okay, the Lagoon Nebula in Sagittarius. This is a large area of glowing gas in H alpha, but this is a glowing hydrogen gas. There's some oxygen in there. This is a broadband red, blue, green image. I think it's with my 5-inch telescope, not sure. But you'll notice a star cluster here, and this bright star here. They are providing the ultraviolet light that's making the gas glow. And the same thing with the dark patches. That's where there's cold, dark dust and gas that's blocking the view further back. This is quite spectacular in a small telescope. Unfortunately, it's getting too low for us right now. Another globular star cluster in Ophiuchus. Okay, let's talk about M13. This is the Great Hercules Cluster. Very dark place. I don't think you can do it here, but very dark place. You can see this naked eye. And this is a view of M13 through my 5-inch refractor with a CCD camera that I owned. It was taken on June 30th, 2018 from my front yard up near the Broome County Airport. This is kind of interesting. Let's see if we go a little bit farther. Oh yeah, just back here, that was at Tupper Lake, New York at the imaging conference where Art and I have been instructors in the past. They have an annual imaging conference. We can go there this year. But here's the same object blown up with just a piece of it. And this is an a very interesting image, and you can do the same thing visually. All those stars you see in there, they're part of our Milky Way galaxy, and they're anywhere from 20 light years away to maybe about 1,200 light years away. That big cluster of 500,000 stars to the lower left, there's a globular star cluster, M13. You think of our galaxy as a frisbee. The globular star clusters are in orbit around the galaxy. Some of them actually go through the center and come back out. And they're some of the oldest stars in our galaxy. And that cluster is 18,000 light years away. And there are two other galaxies in here, NGC 6209. That's about 30 million light years away. And IC 4617 is about 300 million light years away. There's another galaxy, I couldn't even find a reference for it, but this galaxy is 300 million, so you're seeing at least 300 million years into the past there, and you really get the depth. It looks flat on the screen, but you can see the depth, but it's not only depth and distance. Telescopes and imaging stuff is not only a distance machine, making stuff look closer and brighter, it's also a time machine, allowing you to look into the deep past. I can get this same view in my 20-inch Dob from a very dark location like Cherry Springs, and I can see all of those, including IC 4617, which is 16.5 magnitude. And to my surprise and other people's surprise, you can actually see it in the Dob with looking right at it. No imagination or anything. It's definitely there. And that's certainly an amazing view when you look through the eyepiece and you see what you're looking at, or you look at this image and see what you're looking at. And again, this is a picture taken with a 5-inch telescope. It has a 5-inch lens. Here's M13 with the OGS 20-inch, and it's a 1-minute exposure. And it's, believe it or not, color. It's RGB, but it's a color, just 1 minute long. And a much older version of it. We're aiming at improving these images over time. Globular cluster M15, which is prominent in the sky right now, its problem for the visual observer and the imager is it's very bright, but it's very small. So you really need a long focal length to image it, and you need a lot of power to view it visually in your telescope. Here it is again through my 5-inch from my front yard. And there it is through the Kopernik 20-inch. So I'll show you one more group of stuff. I'm going to be getting the cut here pretty soon. This is M16, sometimes known as the Eagle Nebula. You can see the eagle in here. Sometimes known as the Star Queen Nebula. And this is in H alpha, just that narrow hydrogen alpha, deep red, but shown in black and white. And these things here are the famous pillars of creation that appear in the Hubble Space Telescope image that's so popular. There's another similar one here, and these dark cold gas pillars are being eroded away and new stars are forming. And this is with our 20-inch telescope outside. And here's the same thing. What I did, and again, this is narrowband, so I took that deep red H alpha and made it the red color in this image. And I took oxygen 3, which is oxygen with 2 electrons stripped off it, and when they come back in, they put out this blue, green, teal color. So it's blue and green. So I made that oxygen 3 line both blue and green and got this approximate visual, what you would see with your eyeball kind of look to the color. There's a star cluster up in here that has been created out of this nebula, open star cluster. And here's the Hubble Space Telescope coloring. They take these narrowband filters and just randomly assign special colors. And it's called the Hubble palette. So if you see a Hubble image, you really need to, or even a Webb Space Telescope image, you really need to read the fine print. Are they showing you a real color view, or are they showing you this totally fake or view where basically it's of interest to science and a lot of people are impressed with the color, but that's nothing like what you would see with your eyeballs. For instance, they take that deep red H alpha and make it blue. Why they did that, I don't know, but they've been doing it since the early days with H alpha. Drew, just give me the okay, another 90 seconds. The Swan Nebula, M17. Again, it's a star-forming region, and the bright stars in there are creating all of that H alpha stuff. And we need to impress that. Okay, I'm going to show you one more. Again, this is the red part is H alpha star forming region. You can see a shock front in here. These dark channels are the cold gas and dust blocking the view of the nebula in the back. This double star in the center is providing all of the ultraviolet light that's making this gas glow like that. And this blue part is actually just reflected starlight. There's a lot of dust up here. These two stars are very hot and very blue, and you're just seeing the starlight from it. And that's the same thing through my 5-inch telescope taken at Cherry Springs on July 12th, 2018. Again, you'll notice that in this case, we got, I believe that's M18 star cluster here. And you'll notice how there's patches of darkness running through here. That's the same dark material that's blocking the view. There's not fewer stars here. That's just where this gas and dust is blocking the view behind. Okay, well we will we'll leave it there. One thing I'll do is I'll go back and I want to show here's my picture of Kopernik Observatory at 1 million BC with the aliens coming here and Sasquatch. And why am I not in the picture? Because I was taking the picture. But that was 1 million BC. And the Bubble Nebula. And just in case you got stuck with me instead of this guy, but hopefully he will be back the next time, more interesting than I am, and he will be here giving a presentation, but probably next year or the year after. And I guess I'm kicked off the stage.
Well,
okay.
Well, thank you, George. I really appreciate it. Again, we are just so fortunate to have George as a resource here at Kopernik. He's been here since basically it almost has started, and has trained literally dozens and dozens of KES members in astrophotography here. All right, so we're gonna, sorry, hold on a second. Yes. All right, yeah, for those that are interested, we have a planetarium program on the moon that's going to be available through about 9 o'clock tonight. But also, today we are actually celebrating International Observe the Moon Night. Andrew, if you want to mic yourself up here so that, so I'll cue you up. So every year there's an International Observe the Moon Night, and that happens to be today, at least for us. And so we do have a planetarium, portable planetarium that you can purchase a very cost-effective ticket at the register, and then go into physics for that show. But the moon is in fact going to be up. We will have a scope on it at the end of our presentations tonight, and one of the things we'll do on there is we actually have an adapter where you can put your cell phone on there, and we'll arrange it so that you can take a picture of the moon with your cell phone, and you get to take that home with you. So, as I said, we're very fortunate to have an astronomy club, the Kopernik Astronomical Society, that operates out of Kopernik and does an extraordinary amount of work here, especially on Friday nights, but also they come up and do their own thing as well. One of which is Andrew Beck. How long have you been a part of the KAS? Just relatively recently. 2 or 3 years, right? Sort of a George in the making, I will call it. And we asked him to do a presentation on International Observe the Moon night. So are you turned on? Okay. Okay, so I'm going to turn it over to you, Andrew.
All right. You hear me? Okay. My name is Andrew. I am, like Drew said, a newer member of KAS. This is actually my first presentation, so bear with me if I say a lot of ums or but I'll say this is International Observe the Moon night is tomorrow night, October 4th. We're doing our celebration of it tonight. We have a great night tonight. I think the moon is already up, so hopefully you guys can get some really good views of the moon when it comes out later today. So why do we observe the moon? Does anybody have any input? Why do you look at the moon? Yeah. That's a yeah. Oh, yeah. So how far will people go past the moon? And that's a really good question. I don't know the answer to that. If I had a crystal ball, I would answer you. But I hope that nobody has gone much further past the moon yet. But hopefully we will. People have gone just behind the moon, but as of right now, nobody has gone as far as Mars or anywhere near that far. But why do we look at the moon? Why do we look at anything in the night sky? What are some reasons that you have that you like to look at the moon? Yeah. It is pretty. Yeah, absolutely. That is a valid reason. Any other ideas? It is mysterious, yeah. There's not really a wrong answer to this. Maybe we'll get one more input. There's craters. Yeah, you can study the craters and why they occur. I came up with a few reasons. So to explore the history of the early solar system, figure out how things were formed back, billions of years ago, as the solar system was forming, and hopefully we can get some clues to how other solar systems form. We witnessed lunar and solar eclipses. Those are phenomena that we see annually. Who here has seen a lunar or solar eclipse before? A lot of you. All right. Probably in last April. So the other reasons that we look at the moon is to engage with space exploration, Apollo 11, the upcoming Artemis missions, unmanned missions that are currently at the moon or coming up, and because it fosters a connection across borders. And I'll touch on this later. We are all looking at the same moon no matter what country you're in, right? So hopefully that offers connection between yourself and somebody overseas. And for artistic and creative inspiration, like you touched on it. The moon is very pretty. We like to take pictures of it, make art from the moon or based on the moon, and I'll touch on that later. So how did the moon form? We'll look at the early solar system first, and I have a animation here from, I think, NASA's Ames Research Center from a supercomputer. And And we can see this is a Mars-sized object that's about to collide with the Earth. This is the Earth, and this is that Mars-sized object. And it will, let's see, very dynamic. I have the sound off on purpose just so I can be heard, but very dynamic collision here. We have a few objects. We have this, the Earth. We have this object that will continue to collide with the Earth, and this over here will become the moon. This all happened over the course of, probably a few days or a few weeks. And here's another view of it from a different angle. You can see this is this is all molten rock. There's no life on here yet, although there might be some life hidden in the fiery inferno here. Just building blocks of life, water vapor, things like that. And all this is all going to form, all this debris around here will most likely hit the moon eventually and maybe form some of the craters that we see today. So this is the moon as it appears today, the far side and the near side. The near side is on the left, the far side is on the right, and they look very different from each other. Does anybody know or have an idea why they appear different from each other? Yeah. So they are different sides, and that's important. What you might not know is the moon is tidally locked to the Earth. So the same side always faces the Earth. You'll always see that near side. You'll never, from Earth's perspective, you'll never be able to see that far side of the moon. And what happened, as far as I can have done research on at least, the near side of the moon is actually tidally affected. It's affected by the Earth's gravity of the Earth on the moon. So if you think of the tides from the oceans, right, that pulls the water closer to the moon, right? That gravity affects that water. Similar process here, but equal and opposite reaction, right? So the tidal forces of the moon and the Earth are pulling on each other, and they are making the crust of the near side of the moon very thin. And through several impacts, through several asteroids hitting the moon, some magma seeped through, where you see these dark spots. These are the lunar seas. You see these dark spots. The magma seeped through to the surface and then solidified, and that formed these darker regions. Question? Yeah. So why doesn't the moon spin? That's a good question. So the moon does spin. It just spins at the same rate as it orbits around the Earth. Right. So the moon. So when it was forming, the gravity from the Earth affected the gravity of the moon, and the forces balanced each other out in a way that caused it to become tidally locked. It's a very rare phenomenon. I think Mercury is tidally locked to the sun, but other than that, there's very few examples that we actually have of moons being tidally locked to their parent body. There's a question in the back. Yes, so the moon was a lava planet, as we saw in this video right here. The moon actually was completely lava for hundreds of millions of years before it finally cooled and sort of became what it kind of looks like today. And over the years, asteroids hit it and it got all these craters. So here's the lunar seas. All of these seas have names. The most known one here is the Sea of Tranquility. I'm sure most of you know that one. That is where we landed Apollo 11. We have the Sea of Rain, Sea of Cold, Sea of Storms. This is all actually in a packet that's up here in the front. If you wanted to come get a packet later, it shows all the seas, and it also has a really cool visual target. So if you wanted to look at the telescopes later, you can actually spot some of these features. And that packet over there is actually, it actually has a map of what the moon looks like tonight, or technically tomorrow night, but they should be very similar tonight and tomorrow night. Lunar mineralogy. So I wish I had my props here, but so this is a visualization made by Sasha, which is another KAS member and educator here, and she made this cool visualization of what go back. What different mineralogy is found on the moon. So you have Baltic lava flows here, mafic lava flows here, feldspars down here, and this is all through exploration and visual astronomy and things like that. And I wish I knew more about this. If you do have any questions, I would refer you to Sasha. This is all really cool stuff that she was showing me. So yeah, question. Right. So how does the moon glow since it's not a lava planet? So the sun actually reflects light off of the moon, kind of like a mirror, except it's just like, imagine you're just looking at a rock, right? Why is that rock glowing, right? That's just because the sun is reflecting off of it. It appears brighter because it's much bigger in the sky, and it's also dark at night, so it's a lot of contrast. Yeah. So these used to be lava. These areas here, they used to be lava, but they solidified and they became a lot smoother and darker over time. So I'll move on. Lunar libration. So this is actually a cool video of what the moon looks like throughout the year. And you can see the moon kind of does this tilting, so it doesn't perfectly stay straight on towards the Earth, but it does kind of what's called librate or libration, sort of jostles in the sky relative. And you can see the date here. This is January 27th, 28th, 29th down here. A couple of cool things happening here. You can actually see this is to scale. You have the Earth here, and this is the moon, and this is how far away they are perfectly to scale. This 32 and 28 and 30 here, that's how many Earth diameters away the moon is. So, for example, February 28th, it's approximately 28 lunar or Earth diameters away, and so forth. And you can see the orbit. The sun's position is that way relative to the Earth, and you can see the moon right there. And you can see a cool visualization down here that kind of describes the same thing that's happening here. You can also see all the different locations where we landed, as well as a bunch of features that are showing up here. Kind of a cool visualization. So our next topic, how many of you have seen an eclipse? Just, I think I asked this one before, but yeah. So who saw the April last year, 2024, solar eclipse? Was it cool? Was it cloudy? We got some clouds too. We did get some good views. This is members of the KAS took some cool pictures of what it looked like. So here we have just a picture. This is a partial eclipse. This is kind of a cool one. It shows you how dark it gets during an eclipse, and this is approximately what it would look like in the eclipse if you didn't see it in person. This is kind of cool to see, and this is about 3 p.m. I believe it was. So imagine it being this dark at 3 p.m. Couple of nice pictures here. This is all from the eclipse. Who saw the one? So my first eclipse was the 2017. I think it was August of 2017. That was a really good one. Did anybody see that one? Yeah, that's a good one. That was during the solar minimum, I believe, which means this corona right here is at its maximum, and that was really cool. You could see it looked like a hole in the sky almost. Like I was down in Tennessee, and it was clear, and it almost looked like somebody took a chunk out of the sky. Yeah. Yeah. Yep. That's exactly what it looks like. Yeah. Right. So, sorry. So how do the sun and the moon cover each other, even though they're tied to the Earth? Even though they're gravitationally bound? So the sun and the moon, and I'll try to describe this. Am I on video? Yeah. Okay. So the sun and the moon. Imagine my head is the Earth, and the sun is over here, and the moon is over here, right? So the sun and the moon orbits the Earth, right? So occasionally you'll get the moon perfectly covering up the sun, right? Other times when there's not a solar eclipse, the moon might go directly above the sun relative to the Earth, or directly below the sun relative to the Earth. But during a solar eclipse, during these special times, you can see the moon perfectly cover the sun. Does that make sense? So a lunar eclipse. Who saw a lunar eclipse before? These are a little bit more common. More common only because you don't have to be in a specific location to see it. This is Jenny, our live stream astronomer, actually took this video of the lunar eclipse back in March, and you can see this is the Earth's penumbra. This is sort of the atmosphere and the light bending around the Earth, sort of forming the shadow. And then you'll see a darker part come in, and that is the Earth actually covering the moon. The Earth's shadow covering the moon completely. Right there, I think the camera settings changed, so the got a little bit more exposure, or the filter changed or something like that. I'm not quite sure. So this is quite cool. You can see the red glow here, and that does happen in real life. Yeah. Oh, it almost looks like a red panda moon, and you said you've seen that one before. That's really cool. And I think we got another comment that it looks like a blood moon, and yeah, it does. Yeah. Yeah, so a blood moon is somewhat common. I think that's normally when it's closer to the horizon, but this can happen at any time of day. It has to happen at night, I should say, because it has to be on the opposite side of the sun. But yeah, it can happen just after sunset, or even 3 hours after sunset. And here it is. This is the solar eclipse ending, and you can see the camera settings changed. The exposure changed. And this was actually taken here. I think it was from the 6-inch telescope in the dome that you'll probably look through tonight. Yeah, question. Why does the moon appear red? That's a great question. So, to my understanding, the red wavelengths bend around the Earth more. So when the moon is completely blocked out, that red wavelength, compared to the blue wavelengths, for example, bends around the Earth more and hits the moon. And it's reflected back, and you can see that. So here are the upcoming solar eclipses and lunar eclipses. So you have total solar eclipses and annular solar eclipses. Annular solar eclipses are so they don't completely cover the sun, right? The moon does not completely cover the sun. It only essentially envelops the moon in a ring of fire. So you'll see an orange ring surrounding a dark circle, and it's pretty cool. I wouldn't travel, personally at least, I wouldn't travel too far to see those. I wouldn't go to North Africa or Western Europe to see those, but oh, that's a total. I wouldn't go to, but if you want to, that's on, on you. But the annular eclipses, I haven't seen one before, but I heard they are very cool. If there was one in North America, let's see. Yeah, no, none in North America. I would probably go to see it if it were in California, maybe, but I wouldn't necessarily go abroad to see them. Just my personal opinion. Total eclipses, I would probably go. I was actually thinking about going to this Iceland one in 2026. That would be pretty cool. Although I'm not sure if the weather will cooperate. The lunar eclipses are less. Looks like they're a little bit less common up to 2029. But if you wanted to take a picture of this, you're welcome to. Or yeah, it's available online. So I'll touch on this. Are we going back to the moon? The answer is eventually, hopefully. We do have plans on going back. I'll start with the Apollo missions. So we've gone before to 6 times. So you can see a map here of where we've landed. And if you're outside looking at the moon in a telescope, you can try to take a look at these locations. We landed Apollo 11. Neil Armstrong landed right here. Apollo 12. 13 did not land on the moon, famously. There's a whole movie about that. Very good movie. Apollo 14, Apollo 15, and Apollo 16, Apollo 17. So if you wanted to take a look at that, that's also in the packet over there. If you wanted to take a look, and you can kind of see where they landed. If you're looking at the moon, you won't be able to see the flag or anything. The flag and the lander are very, very small compared to the moon. But we'll take a look at it in the presentation later. And here's a visual of the Apollo 11 landing site. So if you were to look in a telescope very close up, you could see, okay, there's a crater right there, a crater right there that kind of looks like that, crater there, this kind of wavy pattern here, and you can see the landing site is right there. So you can kind of triangulate and say, oh, cool, that's where they were. But yeah. Sure. So what you're referring to, you were talking about a robot on the moon or Mars stamping a pattern or a logo on the surface of the planet, and that's yeah. Right. So what you're referring to, I believe, is on Mars, the Curiosity rover. They wanted to put the Jet Propulsion Laboratory, NASA's Jet Propulsion Laboratory logo on the surface of the moon. And I think there was some controversy surrounding that, or some, I'm not quite sure of the specifics, but they did end up putting JPL spelled out in Morse code on the wheels. And so when it drove, the wheels would actually imprint into the surface, JPL. That's not this though. This is just a lunar a ridge on the moon. Yeah. Yep. So yeah, all the robots that we sent to the moon and Mars are still there. We as long as it's not manned, we have not brought anything, to my knowledge, back besides the manned spacecraft. So the Lunar Reconnaissance Orbiter is a unmanned mission. It is in the process of collecting data for manned missions to go. So the mission goals here for the Lunar Reconnaissance Orbiter is to make a simple or to make a 3D map of the moon's surface, to aid in identifying landing sites for the future missions that we're sending there, to aid in the moon's investigating the moon's radiation environment, and prove new technologies in anticipation of future missions. This is a cool feature that I found. This is the quick map, the LROC quick map. And this is, I found it pretty cool scrolling through this. You can actually visualize the moon, and this is what the moon looks like. This is using a lot of real images, essentially mosaicked together, to look at the moon. And you can zoom in quite far here, right? You can see all this detail right here. So you're kind of upside down right here just because we're on the South Pole. I'll zoom in right here. This is, like you might have seen earlier, the Apollo 11 landing site. And you can actually see, if we zoom really far in, you can actually see, I'm going to turn that off real quick, the shadow. That's the shadow of the lander that is still there. This is the descent stage. So we left sort of half of the spacecraft on the moon because we didn't need it anymore, and the astronauts came back in the upper section of that spacecraft. So you can still see that here on the surface of the moon in these lunar images. This is the shadow, and this is the actual spacecraft right here, the bright section. I don't think you can see. This might be, let me see. Yeah, I think this is a piece of equipment here too. You can see right here. But yeah, it's really cool seeing that. So this is like I said, LROC. You can get contours. Let's see if I can do this. Yep, so this is all the contour gradient maps. So each one of these lines right here, I'll take this line for example, this is all at the same height above the moon's sea level, I should say. It doesn't really have a sea level, but the quote-unquote sea level. If you go this way, I'm sure some of you are familiar with these. If you go this way, you're going uphill. If you're going this way, you're going along and staying level relative to the moon. So that's kind of a cool feature that you can see all this contour here. You can also see on the bottom surface of the moon, let me take a look. So I'm going to be looking at the south pole of the moon. This is what the south pole looks like. And you can actually see these sections here. These are lunar landing targets. These are different candidates for where we might land in the future with Artemis. And you'll see a presentation about Artemis after mine. So this is a bunch of this is pretty cool. Did you have a question? So this hole here. So this is probably distorted just by the looks of it. I could be wrong. So we're hoping, I guess, the guidance computer will keep it out of any danger or any rough terrain or anything, and hopefully it will land on a flat surface based on lunar imagery. So of course they have much better information than this, and so they can pick a specific target. For example, right here is a nice spot, or what. I'm not really yeah, right here could be a good spot. I'm not really sure exactly where they're targeting for this area here, but yeah, definitely some terrain features, some big boulders to watch out for and stuff like that. So good question. This is online. So if you look up LROC map, you can look up that. I don't know if it's downloadable. So I'll play this video. It's just a sightseeing tour of the moon. A lot of this is, I believe, animation, but a lot of it does use real imagery. And the animation is based on real data. So this is just a tour of some of the really cool features of the moon.
To nearly everyone, the moon appears to be a sterile, gray, unchanging world. But while the moon has remained largely unchanged during human history, our own understanding of it has evolved dramatically. Thanks to new observations, we now have not only unprecedented views of its surface, but a whole new tour of the moon that shows how both it and other rocky planets in our solar system have been shaped over billions of years. We'll start with one of the largest impacts, Oriental Basin, a feature that's as wide as the distance from New York City to Cincinnati. Using new elevation measurements, we can clearly see the effects of what is likely the last giant impact event in lunar history, with its outer mountain rings rising many kilometers above the lowest points inside the crater. The interiors of some craters in the moon's polar regions, like Shackleton, haven't seen sunlight in over 2 billion years. However, new measurements have created our best yet maps of these types of craters, allowing us to see deep into the shadows of this surprisingly young-looking impact crater in the south that's more than twice as deep as the Grand Canyon. Some impacts are invisible for other reasons. Although the ancient South Pole Aitken Basin is difficult to see from orbit because it is so large, new LRO topography maps reveal the largest impact basin in the Earth-Moon system, measuring several kilometers in depth and around 2,500 kilometers in diameter. Only the Hellas Basin on Mars rivals it in size. One of the youngest large-scale impacts on the moon is the Tycho crater. This fresh crater may have formed only 108 million years ago, when dinosaurs roamed the Earth. We now also have an extreme close-up view of the crater's central peak, revealing a mountain with sharp edges, building-sized rocks, and a central boulder about the size of a baseball stadium.
Very cool. I don't know if you'll be able to see the boulder. I kind of doubt it, but it's a little bit small.
The Aristarchus Plateau is another recent lunar formation that has long interested scientists and astronomers. The crater itself formed in the same era as the Tycho crater, and what appear to be snaking river valleys were actually carved by ancient lava flows. Next, we arrive at Mare Serenitatis on the near side of the moon. In December of 1972, the crew of Apollo 17 landed in the Taurus Littrow Valley, marking the last time humans have visited the surface of the moon. With images from
So these right here you can see. Who knows what they are? Yeah. Yeah, what are they? These little trails here. Yeah. They're footprints. Yep. Footprints and rover marks. It's hard to say which ones are which, but these are definitely, you can see right here, there's two side by side. So that looks like rover. This looks kind of like footprints, so it's hard to tell. But these are, remnants from when we went there.
Polaro's narrow-angle camera, we can clearly see the evidence of that visit. In this image, you can easily see the base of the lunar lander, along with the lunar rover, parked far from the blastoff zone. You can also clearly see the astronaut trails and the wheel tracks left on the lunar surface. We now head to the far side of the moon, which cannot be seen from Earth. Our first stop is the Compton-Belkovich region, which shows evidence for young volcanic activity in the far side highlands. This feature is unique not only because it is isolated from other volcanoes in the area, but also because it is located nowhere near the Maria, where volcanoes are usually found. Also, on the far side, we find the Jackson crater, which, like the Tycho crater on the near side, has an extensive and complex ray system. In fact, this crater is often considered to be like a twin to Tycho. Finally, the Tsiolkovsky crater stands out as an excellent example of a far-side crater filled with a sea of ancient lava, known as a mare. It is particularly interesting to scientists and other observers because of its isolation from other similar craters, as well as its beautiful central peak. As we continue to study the moon,
So quite a few interesting views there. Yeah. Yeah, so I'm actually about to go into that. You said that scientists and engineers are figuring out how to go back. So this is Artemis 1. This actually launched a couple of years ago now, and it was a successful mission, launching in November of 22 and coming back about a month later. And it certified the Orion crew capsule and the Space Launch System for crewed flights. You can actually see a model of it right here. This is all to scale. This is how we went to the moon back in the 60s and 70s. This is the Apollo Saturn V rocket. This is the Space Launch System that astronauts will take, I think it's scheduled for next year, to the moon, lunar orbit. And then this is how we'll land on the moon, is SpaceX Starship. So you can see, I think I can remove this. This is the actual section, or at least a model of the section that will land on the lunar surface. Similar design. So this is all to scale. You can see, I think there's people down here. They're about 1/8 of an inch tall, to scale, but kind of cool to see. So Artemis 2 is the first mission to carry humans back to the orbit of the moon. It will not land on the moon, but it will confirm that all spacecraft systems operate as designed with crew aboard. These are the 4 astronauts designated to go. And that's launching in April. And we'll actually learn a little bit more about this through the next presentation, and all 3 of these missions. And I'm not sure if he's going to touch on Gateway, but okay. So Artemis 3, mid-2027, is when we plan on returning humans to the moon. And this will return, hopefully, a lot of rocks, samples, retrieve samples, study the geology, and collect data from the South Pole and those landing sites that we mentioned earlier. So, yeah. Yes, there is. So you asked, is there a reason that they're targeting the southern region of the moon? So in a lot of the craters on the southern pole of the moon and northern pole, there is actually solid ice found in there just because they're in shadow 24/7. The sun never touches the bottoms of those craters, so that's a really interesting target to find solid water, ice in there. So last year in 2024, this is sort of the results from last year's International Observe the Moon. There were 1,497 events, total of 6,535 independent observers and events occurring across 7 continents, 127 countries, and all 50 states. This year, last time I checked, which was last night, there are over 1,200 International Observe the Moon events. Ours is taking place tonight, which is a day early. I'm sure this number from 1,200 will go up probably closer to 1,400 by the end of, or by tomorrow night. But you can see, I actually really like this map, and this sort of touches on another point that I made earlier. This map, if you notice, does not have any borders, and I think that was intentional on the designer of this map, in that it is International Observe the Moon night, right? It doesn't matter if you're looking at it from upstate New York, or if you're looking at it from, you know, the UK, from South Africa, from, you know, Ukraine, from the Middle East, right? We are all here on Earth looking at the moon together, and hopefully you can feel a connection across borders, across cultures, that we're all looking at the same thing and all appreciating, you know, the beauty of the moon. So do you find the moon inspiring? And I think you touched on it earlier. So I found a lot of artistic representations on the moon, different artistic takes on the moon's surface, right? A lot of these you'll know. Artemis, very good book. Andy Weir, highly recommend. All these are really, you know, some of them are famous views of the moon. This one especially, this one is actually, I believe that's a KAS image that I got. This is an ancient, I think it's, I want to say it's Neo-Babylonian king here. A couple of modern images here, and a poem. So some really good, some really good stuff here. And hopefully it inspires you if you want to, you know, take photographs, paint the moon, whatever, you know, whatever floats your boat, whatever medium you want to, you know, show the moon in. I hope, you know, you do that. So tonight is a really good night. I hope you guys take the opportunity after our next presentation to step outside. It's, you know, clear, at least last time I checked. And yeah, any questions? Yeah. Actually,
Hold on a second. Let me run over here with my mic so that people on the live stream can hear it.
I have a question. Is the moon one opening around this Earth, or is the moon one moving far away from Earth, like it's leaving us slowly?
right. So the moon is in orbit of Earth, and we are physically attracted to the moon. It is receding away from us very, very slowly. You won't notice it in your lifetime, which is the good thing. Probably in a few million years, I believe, is the timeline for when it's going to recede beyond our gravity. I think it's moving away at like 1 centimeter every year, so nothing to worry about. Yeah.
Oh.
How I forgot what I was gonna say.
When you think of it, just raise your hand again. Any other questions? Let me just check the chat, the YouTube chat, if there are any questions there.
Oh yeah, YouTube chat. Hopefully you guys can go outside and observe the moon too, if it's clear. Yes.
So one of the great things about doing this on a live stream is that literally people from around the world are able to to view. And in fact, one of our top viewers is Lindsay from Adelaide, Australia, who's actually watching right now in Adelaide, Australia. So it's actually Saturday morning for Lindsay. So can we all get everybody to say hi to Lindsay?
Hi, Lindsay.
All right, very good. All right, now you got your question again? All right. All right, well, Andrew, thank you so much again for very well, a nice breadth of information and well researched. And so what we're going to do is we're going to take about a 10-minute break. We're going to shoot to start up again at 8 o'clock. We are very fortunate, well, the Southern Tier has had a very extensive connection to the space program from its very beginning, including link simulators that were built here and trained the astronauts. For those that maybe are here for the first time, you'll notice we have a little astronaut Hall of Fame, and it shows the 4 astronauts that grew up right here in the Southern Tier. There's currently a flight surgeon who grew up in Johnson City. Dr. Joe Dervay is he's basically a doctor to the astronauts, still at Houston. But also there's a gentleman who grew up in Johnson City, Gary O'Neill, who works at NASA, at least up until a couple of days ago. Well, actually, he actually is still working there. He's one of those people that need to sort of continue to work, and he's actually working on the Artemis program. And so I'm going to set up a Teams session. He's going to remote in from Florida, and so we're going to give you about 10 minutes. We're going to start just around 8 o'clock. So give you an opportunity to do a bio break. Restrooms are down the hall to the right, and so come on back at 8 o'clock, and we'll have Gary O'Neill up on the screen.
all processed through this building before being launched on the shuttle to be assembled in orbit. Of course, it's been up there for over 2 decades now. Pretty wild to think that a lot of the kids in the room there and a lot of kids in high school today, throughout their entire life, we've had human beings in orbit around the Earth, working and studying a lot of scientific things up there. SSPF here. Over that way to my east is the operations and checkout building where the Orion capsule is being processed and integrated and getting ready to launch. And then directly behind us, dark now, and there's trees there anyways, the vehicle assembly building a few miles away up that way. The SLS pads over there, the Falcon pads over next to that. So right in the center of all the activity here. So let's talk about Artemis tonight. And if you have any questions, just yell at Drew and he'll get you a microphone so I could hear you, okay?
All right, very good.
So why are we doing this? Well, there's 3 tenets to everything that we're doing at NASA. Science, of course. We're going to go to the moon and beyond to understand more about our solar system, more about our universe. One of the things about Earth with its dynamic environment and all the nature system that's going on, it tends to either destroy or hide a lot of the evidence of what happened early in our solar system's existence. The moon and Mars, to an extent, are kind of pristine. We can go there and see basically a record of history of what's happened in our solar system. So that'll be exciting to really be able to go there, study that, learn about ourselves, learn about the solar system, learn about the universe. Of course, NASA, one of our main drivers is to inspire all the young people that we have in the room there. We do these challenges, you know, going back to the moon, going to Mars, to spur that interest, to inspire the youth to get into STEM and make our nation great, right? I mean, our kids are our future. We want to get them into science so we can learn more and more things. And of course, national posture. We take great pride in our Apollo history, winning that space race. We want to continue to set the standard and conquer these frontiers as a nation because we are doing so in a peaceful way. And you'll see later in my presentation how the world's kind of rallying around this Artemis campaign to achieve all these tenets. And of course, that Venn diagram on the left there, they all come together to show our nation's leadership, a lot of employment, smart people, really good careers, and all to improve our human condition again, and understanding what's going on around us in our solar system and universe. So why the moon? Why not go right to Mars as one particular billionaire wants to do, right? It gives us the opportunity to prove out the systems, prove out our capabilities in running and operating those systems, and just understanding the operational paradigms that you need to execute when you're at some distance away from Earth. And as you heard in the previous presentation, which was an excellent setup for me tonight, we know that now that there are resources on the moon. There are volatiles in those craters that are permanently shadowed, oxygen, water ice, metals that we can use and take advantage of, not only to live there for longer durations, but also to maybe harvest, fuel our rockets, 3D print from the lunar soil, different things that we can then take from the moon further out. It's very expensive to get a lot of mass, a lot of weight off of the Earth. We've got a fairly deep, what we call gravity well. The Earth doesn't want stuff to leave. So it takes a lot of fuel, a lot of energy to get out of our Earth atmosphere, out of our gravity well. If we can take advantage of the moon, build things there, it's a lot easier to get away from the moon and take that mass and our equipment out to Mars. Plus, the moon is fairly close, right? 250,000 miles is somewhat close compared to Mars. We want to test things out at the moon first before we make that long journey out. This video, I hope it's playing all right. There's no sound, but it shows that throughout history we've been in Earth orbiting, human spaceflight Earth orbiting activity. Going to Mars, we are going outside the Earth-Moon system, right? That's hard. As you can see, when the Earth and the Mars are in their orbits, crew has to leave at a fairly specific time to try to catch up to where Mars is without using too much energy, which means a lot of fuel. So we got to line up, fly our trajectory to kind of intersect Mars. If we want to stay longer or for a long duration, we're going to have to wait for the alignment to come around again for another 4 years. Or, as this trajectory shows, this shows a relatively quick visit. I think what it says, it'll say soon around 50 days, I think, in the vicinity of Mars. We can make a quick visit, leave the Mars system again, and kind of swing out and try to catch up, with Earth again. What this means is it takes a lot of time. I think that at the end here, it's a 2 to 3 years of total time to get out to Mars and get back to Earth. So not the great place, not a great distance to go find out and learn things as far as how your spacecraft runs, how do you live and sustain yourself for a long period of time. So we want to do all that stuff at the moon first. Just a few days away travel, a lot better than trying to make mistakes and learn out at Mars. Let's do it at the moon first and use those resources I talked about. Any questions there before I go on?
All right. At this point, we're good. Press on.
Okay. So again, we want to go to the moon. There's a lot of commonality about what we'll need at the moon, what we'll need at Mars, right? All these things. Aggregation of things in deep space. We're going to build a station out at the moon, an orbiting station. You'll hear about that coming up, called Gateway. Habitats, long duration habitats. How do you run them for, we've done it in Earth orbit, fairly quick to get stuff to and from, fairly quick to send parts up when they break. How do you now run these systems further distance out? How do you make them autonomous to try to fix themselves rather than being able to send up something real quick? Orbit to surface. We're going to be doing a lot of surface activity at the moon as practice to doing a lot of surface activity at Mars. That's a challenge in and of itself. My project, Deep Space Logistics, Commercial Resupply and Fueling. How do we use our industry, which has been delivering cargo to the space station for a long time now? How do we leverage them to do resupply at the moon and beyond that? Of course, we're going to learn a lot about crew health and performance. Deep space is a different environment than low Earth orbit where the space station is. Radiation's a big deal. We'll be outside the protective bubble of our magnetosphere. So radiation is going to be something we're going to be studying a lot with our crew. Getting new spacesuits, better, more efficient spacesuits, lighter spacesuits. And of course, throughout all of this, the commercial sector is really helping us do that. When we get there, when we get to the moon or we get to Mars, mobile operations, what would we be without our cars here on Earth, right? We're going to want to put a lot of rovers on the moon to help us go get stuff, to help the crew go out and explore things and get those volatiles that are in the crater so that we can actually utilize them. Planetary protection is a big deal at NASA. When we do interplanetary missions, we take great strides to not pollute the planet we're going to. Really clean rooms to make sure no little bugs travel with our spacecraft to Mars, those kinds of things. Now we're going to go back and forth, so kind of we don't want to bring them back either. Whatever we find out there, we're going to be very careful about the planetary protection between our planet and the planets we're visiting. I mentioned human robotic exploration. We've been doing that for a long time now. Proud to have been on the launch team for Curiosity rover. They're out there kind of doing the surveying for us. We're going to continue to do that even if we have a human presence on the moon and a human presence on Mars. Still going to have our robots going out there and surveying for us before we go to more distant locations on either planetary body. Then just, like I said, learning how humans can survive and thrive in a partial gravity environment. We've learned a lot at the station, as I said, we got to keep learning, right? So we're going to do all that at the moon because, as I said, the round trip mission to Mars takes 2 to 3 years, and we can't turn around if something's not right. So we're going to do all that stuff, learn as much as we can around the moon, take advantage of the resources there before going that further distance out. And I'm going to pause after every slide in case you have questions.
All right. You got them.
Okay.
Nope. We do have a question. Hold on a second.
All right, go ahead.
Define volatiles, please.
You say that again?
Define volatiles.
Volatiles are things that would want to vaporize, right? So as it was said earlier, deep in these craters that are never sunlit, temperatures are minus 300, 350, something like that. Water doesn't want to vaporize. Other gases don't want to vaporize. So we can go there, we can get them, then put them to use in our systems or as life-sustaining gases. Stuff that wants to boil away, put it simply. Okay.
All right.
All right. So Artemis.
Go ahead. Go ahead.
Let's get to Artemis. Okay. These are all the elements of Artemis. It's a complex combination of different systems that we need to execute these missions. Here at Kennedy Space Center, Exploration Ground Systems, those are the systems that launch, test, and operate the SLS system, Space Launch System of Others. Of course, the Space Launch System is flown once, that was mentioned earlier. It's getting ready to fly again early next year. As I mentioned earlier, the Orion spacecraft is across the parking lot, being ready for flight, integrated with that white piece that you see on the left there. The capsule's on the right. There's a big white piece on the left. That's the European Service Module that the Orion capsule's launched to, mounted to at launch, flies with it. That European Service Module provides the propulsion, the power, and the communication for the crew that's in the capsule during their entire flight until they're ready to re-enter to Earth. Of course, we've got to communicate with them, right? I mean, we have a deep space communication system. We're always having to improve that. We're already showing with all the activity we want to do out there, that system is going to be stressed to its limit. So there's a lot of work going on there to increase its capability. The human landing system was mentioned a little bit ago. I'll talk a little bit more about that, but we got 2 landers in the process of being built. And I'll tell you when and what those are a little bit more coming up. Surface operations, of course, we got that surface mobility rovers and such already in procurement to be produced and delivered. New spacesuits I mentioned, and we need a whole lot of infrastructure. If you're going to stay at the moon longer than the Apollo, go plant a flag and leave, we're going to need a lot of infrastructure, landing stuff leaving the surface all the time, communications, across the planet, up and down, back to Earth. So we got to build that infrastructure. And then my favorite piece of the architecture is the gateway, because that's where I work. The Lunar Orbiting Space Station that we're going to be building, and I'll talk a little bit about more about that coming up. Pause again. Questions? Okay.
Nope.
All right. So you already heard a little bit about this. Artemis 1, first mission, flown late in 22. Successful, uncrewed, was the SLS rocket, the Orion crew spacecraft, and of course the ground systems to get them launched and going. You may have heard some things about the heat shield. That's why we flew the test, right? That was a big thing to test for Artemis 1. How well does the heat shield do? We learned. I mean, one of the things about that, the way they returned for Artemis 1, it was called a skip trajectory. They came back and kind of hit the atmosphere, skipped back up, and then came down, trying to bleed off some energy before they came down. As I understand it, that particular trajectory, what we call thermal cycle, the heat shield. It got hot, cooled down again, got hot again, and that caused it to kind of crack and kind of chip off a little bit. So they studied the heck out of that over the last few years, and they got it ready to go. Again, that mission was successful. If the crew were on that reentry, they would have been just fine. The heat shield did its job. They're just going to optimize the design so it doesn't do that again. And I don't think they're going to do the skip trajectory again. I don't think. But anyway, great flight. Awesome performance by the rocket. Awesome performance by just about everything. Success. Artemis 2 is coming up. Crew flight. Not a landing, but a crew flight. Test out. I have a video. It probably won't work. But they're going to test out the systems with crew interacting with the systems and doing some different things. Artemis 3 will be our first landing. That'll be the big one, right? The history-making one. And there, the new elements will be human landing system and the spacesuits to get to operate on the surface. Then at Artemis 4, we start assembling our station called Gateway. All through these, by the way, even on Artemis 1, we flew science. The SLS rocket deployed what we call some CubeSats. and it has some payloads permanently mounted to it that was collecting science all along the way. So every time we fly, I don't care what it is at NASA, we're always trying to find spots to insert science, kind of piggyback along on the ride. All right, Artemis 1, again, mission complete. The Artemis first are listed there, uncrewed flight test of the SLS, the Orion, ground systems that operate them. I told you about the heat shield, and we did all that science. And you can see what the new elements were there, not the least of which was the mobile launcher one and its upgraded ground system. We had to, you know, from the shuttle days to this, we had to build a whole new launch structure that you see there next to the rocket in the picture. Artemis 2. I'm not even going to try the video. Artemis 2 is going to be a mission with crew, like I said, the same rocket, the same Orion, the same ground systems, but with crew on board. We'll have the launch abort system attached. That's a system that's on top of the rocket. If something goes wrong during the ascent, the Orion will separate from the rocket that's in trouble. The launch over to abort system will pull Orion away, fly it away quickly, and let it come back into the ocean to save the crew. Once they're in orbit, they're going to do what we call proximity operations demonstrations. Obviously, to do landings, we're going to have to rendezvous the crew with the lander, later on with the gateway. So testing out those systems and how well it does to rendezvous with another object in space, track it, approach it, to the point, I don't think they're not going to dock to anything in Artemis 2, but I'll test all those systems up to that point. How does the thing maneuver? How does it navigate? How well is it controlled? So they'll do that before they leave Earth orbit. They'll do that using the upper stage of the SLS rocket as a target. Of course, we're going to be collecting a lot of human data as they fly to and from the moon, all the way through to reentry and splashdown. Of course, we're also going to be flying science and technology demonstrations along with that. Again, the new elements for Artemis 2 will be the Orion life support systems, new egress system at Launch Complex 39, and they've done some ground system updates with the hydrogen system. And again, as I said, we're using the same rocket in the Block 1 configuration, the same Orion, the same mobile launcher. What's the status today with Artemis 2? SLS, with its core stage, its upper stage, and its SRB, solid rocket boosters, all stacked in the vehicle assembly building out at a couple miles that way behind me. And you can see some pictures from it there. Everything's stacked except for Orion on the top. That crew capsule is finishing up its integration with that European service module I mentioned. And that'll be integrated with what you see in the picture there this fall, later this year. And again, as you heard before, the launch is planned for no earlier than February, certainly no later than April. Get that crew off and get this test flight done. Artemis 3, again, the exciting one. Here's where we land. Human landing on the South Pole. That's what we're targeting. You've already heard it. Through a mission I also worked on back in the day called LCROSS, Lunar Crater Observations Sensing Satellite, something like that. That was the one, if you remember, we flew an Atlas V, which had LRO, which was spoke about earlier, on top of this LCROSS spacecraft. They launched together. LRO separated, went to the moon, got in position, and started doing its observation, where you got great pictures of the previous landing sites. LCROSS stayed attached to the rocket upper stage, took a ballistic transfer, a long transfer to get to the moon. And when it got to the moon and started approaching the moon, LCROSS separated from the upper stage. The upper stage impacted. LCROSS and LRO observed the impact of the upper stage, studied the plume that came up, the plume of dust that came up from the South Pole. And then LCROSS followed it with its own impact, and LRO studied that as well. Through studying that plume is where we discovered that those volatiles exist in the craters, the permanently shadowed craters of the South Pole. So LCROSS was the critical mission for us to set off on this Artemis campaign for sustained presence at the moon, because we have resources there that we can leverage for that sustained presence and to fuel our rockets, the breathing air, water, it just opened up the possibilities for this Artemis campaign. Artemis 3, full up Orion rendezvous and prox operations with a docking system to rendezvous and dock to the Starship human landing system. And they'll take that landing system down to the surface. Same Block 1 configuration of SLS as we're flying through at Artemis 1, and then we're flying in Artemis 2. Same Orion, same mobile launcher. Looking for mid-27 for that launch. Oh, I skipped right over the near rectilinear halo orbit, NRHO. That's where all this is going to happen, the orbit around the moon that we're going to utilize. It's the same orbit that Gateway is going to utilize, and I'll talk about that in the next chart if you're ready to go on. Any questions about Artemis 3? Okay.
Oh, yes, we got a question.
Go.
Two questions. One, I was wondering, how long is the duration when the two astronauts go down onto the moon? How long are they staying?
About a week. And that is determined by the orbit, the period of the NRHO orbit will be in. The Orion will be in this NRHO orbit, which has a period of about 6.5 days. So they'll leave that orbit to go to the surface, do their thing, and leave the surface in time for the next passing of Orion for them to rendezvous with on the way up. So it'll be 6.5 days. That'll be our first one. Our plan is to extend those stays to 30 days, 60 days. As we learn and grow and build up that infrastructure, we'll stay longer and longer. The first one will be 6.5 days.
Okay.
Did you have another question? That was
Yeah,
good.
well, my second question was, is the Artemis program going to have a lunar base, or is it just going to be a lunar orbiting station?
Both. It'll have both. We are planning a base at the moon. We gotta get the station up there to aggregate everything we need. But yeah, with the rovers that we're going to put down there, we're going to build pads down there. We're going to try to build habitats down there to have a permanent, sustained lunar base on the South Pole. That's the long-term plan.
All right, very good.
Okay.
Press on.
Yeah. So the orbit, Gateway's unique orbit is that NRHO, near rectilinear halo orbit. It's a polar orbit, number one. Again, we're targeting the poles where the volatiles are in those permanently shadowed craters. So it's a polar orbit. It passes over the north and south poles, makes it easy for us to leave that orbit and get to those poles, really anywhere on the moon's surface, but targeting those poles where we want to do sustained operations. It's an easy orbit to get to. And easy, I mean, by the energy it takes a vehicle to travel from Earth. Uses most of its energy to get out of the Earth's gravity well. But once you're out of it, it's fairly low energy to get into this orbit. It's fairly low energy to get out of the orbit, whether you're going down to the surface or to Mars. So again, it's a waypoint either to go to the surface of the moon or a waypoint to aggregate and go further to Mars. It's a great environment for communications. Earth is always in view. So we always have a direct to Earth comm path, which is very important, as you would think, for sustained operations. That will be one of Gateway's functions in its early life. Before we have a comm network built up out there, Gateway will be our comm hub. Certainly science is going to be a great platform for science. Outside of the Earth influence, a lot of radiation studies we already have payloads planned for Gateway on its first elements being delivered that will study, monitor, and measure the radiation hitting it. So we can understand how well our astronauts will do in that environment. And then again, it'll be orbiting. We'll be able to study the far side of the moon and just learn more about the environment we're going to build our bases. And again, that full orbit around, it takes 6.5 days for the orbit we chose. So yeah, they'll leave at one point in the orbit, go to the surface, and then the station or Orion will pass around. When it starts to approach the point they left, they'll launch off the surface to rendezvous with it at the same point in which they left. So that's what defines the first stays on the surface, 6.5 days. Okay.
All right.
Oh, I didn't realize I had a video of what the orbit actually looks like. It's a highly elliptical orbit with a close pass to the moon at its closest point. It's about 1,000 kilometers above the moon, and it's like 70,000 kilometers away from the moon at its farthest point. But again, a lot of advantages to it. It's an odd orbit. One of the advantages I didn't mention, it's very, very stable. What does that mean? We don't have to use a lot of fuel to stay in that orbit. So for a station that wants to be there a long time without a lot of maintenance, a lot of refueling, it's very stable. It wants to stay there by and large. Okay.
Actually,
The
Gary,
HLS.
Gary, actually, I have a
Yeah.
question.
Sure.
In bringing Gateway to the moon, is it going to be a one-shot deal, or is it going to be a multiple launch to put the entire Gateway together?
It's going to take a lot of launches, and I'll have a little bit of that coming up, Drew.
All right. Sorry.
Yeah, and that comes back to the capability of our launch systems we have, right? You can only get so much mass up at a time. So I'll have a kind of a cadence of how it's built up coming up shortly.
All right, very good.
So the human landing system, talk about big things, right? We got 2 landers under procurement being built today. I'm sure you all heard about Starship by SpaceX, right? So the Starship lander is a variant of the current Starship that you're seeing SpaceX fly every once in a while. I think they got another one coming up right there in a couple weeks, right? Been flying those out of what's now called Starbase, Texas. What you see flying today with the fins on it, I guess the model was shown in the previous presentation. Those are actually the tankers. The way the Starship system will work, they'll fly what's called a depot, another version of Starship, a big tank will be put into low Earth orbit. Then it'll be kept full of its fuel, oxygen and methane, by frequent flights of these tankers, which are the ones that have the fins. They'll fly the tankers up, transfer the fuel into the fuel depot. The tankers with those fins re-enter and get reused, fly back to base, get reused, and they just keep flying tankers. They keep the depot full of gas, just like those tanker trucks going to the gas station to keep the gas tanks full, right? The Starship lander, which you see an image of there on the left, is another version of Starship. It's got all the pressurized system inside for crew to live in. It will fly to the depot. It will refuel at the depot and then go out to the moon to do its thing. So really there's at least 3 versions of Starship planned. Actually, more than that, there'll be other versions that'll fly spacecraft to be deployed like our rockets do every day, pretty much every day now. So Starship is a general name for the whole system of different variants of this system. What's interesting about this system is it's a rocket upper stage that's going to become a spacecraft, a long duration spacecraft. So it's a new paradigm for us to understand how a rocket stage, you can see its aerodynamic shape, right? How a rocket stage can become a long duration spacecraft. I did have the pleasure of visiting Starbase this summer and stood inside a mock-up of the lander. I call it a cathedral. It's a game changer as far as what the crew will have to live in. I think it's designed to carry up to 100 people, so that's how big it is inside. Interestingly, though, that brings its own challenges. How do you operate in zero gravity in such a large space? Imagine yourself getting stuck in the middle of a big area and you got nothing to hold and move yourself, and you're trying to basically swim in air. Not sure how they're handling that challenge yet, but it's just huge. On the right side, the Blue Moon lander doesn't get as much press, but it's also under development by Blue Origin, which has a massive complex right outside the gates here at Kennedy Space Center. It will fly, it'll launch on the New Glenn rocket. That's Blue Origin's new rocket. It flew successfully earlier back in January this year. It'll launch again, hopefully soon, maybe November, with a mission called Escapade, which is a couple of spacecraft going to Mars. And then the third launch, which will come early next year, will launch a Blue Moon lander. It's their Mark 1 lander, which is a cargo version of this lander that would be planning on taking about 3 tons of supplies down to the surface. So Blue Origin is quietly moving along and getting their rocket flying and getting their lander built. So we could see them put a lander on the moon at the South Pole sometime next year. Very different corporate strategies in achieving success. Starship, SpaceX, they're a fly it, didn't work, fix it, fly it again, didn't work, fix it, and they keep doing that. Blue is more of let's get it right. First time, you don't hear much about them. They maybe more of the perfectionist is going to fly right the first time, and it did back in January. There's different strategies. Both are fine. Watching starships launch and fail are kind of fun to watch. But they're learning everything, and each time they do it, it's kind of fun to see them do the way they do it. Any questions on the landers? They're huge. You can see the little astronauts down there. You saw, I guess, the previous speaker showed scale models there in the room. I guess the big difference to me, the blue moon lander, the crew's down at the bottom. See the windows down there behind the text? Oops. Sorry, losing control of my pointer. The SpaceX Starship version, the crew's up at the top, and there's an elevator that takes them all the way down to the surface. Again, different ways to solve a mission. It's interesting to see how these companies do it.
What happens when the elevator doesn't work? Is there stairs?
We have the same question, Drew.
Yeah.
All
right. Glad to know I'm not the only one.
Yeah, I mean, it's again, I'm not going to, SpaceX is awesome. I'm so impressed by what they do, and visiting Starbase, it was an amazing place. It's just incredible. Yeah, how do you get the elevator, make sure the elevator works? The mechanisms are always hard to deal with when you have, all the environments of launch and space flight, and now you have dust and all that good stuff. There's that, and it's pretty tall. I don't know if you paid attention to some of the missions that have been trying to land on the moon. They tend to tip over because the surface isn't very level and there's lots of soft regolith there. It'll be really interesting to see them test this out. I think the center of gravity of that is really actually very low. All the engines are down there. Whatever fuel is remaining is all the way down there. There's gravity on the moon. It'll be down low, but still, that'll be one of their challenges that they'll, aside from refueling in low Earth orbit, one of the many challenges they'll have to get this thing to work. But, SpaceX does get it to work eventually. So I have confidence that they will. Okay. So here's the Artemis Gateway assembly, Drew, to answer your question. So
Okay.
PPE and Halo, what those are, PPE is the power and propulsion element. It's basically what it says, right? It's got the power system, it's got the big arrays that roll out. Those arrays are about a football field in size. They're big. It's got all the communication systems on it. And it's got thrusters and prop on it. It uses solar electric propulsion to get out to the moon, which uses the ions of xenon as thrust. Very, 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 very efficient. It's not going to pin you in your seat. It's going to take, once it launches, it takes almost a year for it to spiral out to the NRHO orbit, but doesn't use a lot of fuel to do it. So that's the trade. You can get real good fuel efficiency, but you won't get there very fast. Those will launch on a Falcon 9, or actually a Falcon Heavy from here at 39A, and using an extended fairing, the PPE and Halo. Halo is actually a pressurized element. It's the first habitat that'll be up there that the crew will be able to live and work in. They will launch together. They're permanently mated on the ground. They'll launch together on that Falcon Heavy. And once it's delivered in NRHO, Gateway becomes a thing. So again, that's planned for 2027. Artemis 4, that'll be, Artemis 3 happens in between there, right? The first landing, that happens without Gateway. Artemis 4 will be another landing. You see Orion there in the picture. Orion will come, and with it, it'll bring the International Habitat Module, another habitat for the crew to live and work in. They will launch on a upgraded version of the SLS. They'll launch together. They will rendezvous in Earth orbit. Orion will separate from the SLS, then turn around, come back, and extract the international habitat, much like in an Apollo way that they did it with the service module and the LEM. Then it'll take it out to NRHO, meet up, rendezvous with Gateway, dock IHAB and add to that system. The other element that shows up for Artemis 4 is our logistics module. See a version of it there pointing downward at the floor there. Bringing all the supplies that the crew will need. It'll also bring systems that could not be outfitted on the Halo and IHAB because of mass limitations. And the Falcon Heavy, all these rockets have a certain performance that they can get out of Earth's gravity well. The elements of Halo and IHAB are currently a little bit over mass, so they have to offload some things. They'll put them in our logistics module. We'll deliver them while 2 crew go to the surface. 2 crew will outfit those systems on the Halo and IHAB as part of Artemis 4. Then a year or so later, Artemis 5. And we keep adding to the stack. Orion will not bring another element called the Esprit refueling module. That's, you see Orion there at the bottom of the picture. There's that Esprit refueling module is between it and the axial axis of Gateway itself. That module has extra xenon to refuel the PPE, for example. Another thing that the ERM has, windows. It's the only element on Gateway that will have windows other than Orion when it comes. So that'll be a nice add to our home, away from home, for the crew to have windows to be able to see out. We also, on our logistics module, which is now in this configuration over on the left there, it'll be our job to deliver an upgraded version of the Canadarm that you have seen in the past on the space shuttle, that you see on the International Space Station today. An upgraded version of that. It's actually 2 arms, a long arm for long reach, and then it has a smaller arm with a lot of dexterity, a lot of degrees of being able to manipulate itself. We'll deliver that as part of our logistics service to equip Gateway with an arm. And then Artemis 5, we add yet another element called the airlock. The airlock is an element that will allow the crew to do EVAs, extravehicular activities, get out of the station, do maintenance. We can take experiments in and out of the pressurized space. So Orion, once again, will deliver the airlock and will deliver logistics. And at that point, Artemis 7 forward, that is the sustained version of Gateway that'll remain in Earth orbit, or not Earth orbit, lunar orbit. Design life plan for 15 years, but NASA, you've probably read it in the press. We tend to overdo things. We always get extra life out of everything that we have our hands on. Planning for 15 years, we expect it to go longer than that, especially with the refueling that we deliver. And every one of those missions, Artemis 4, 5, 6, and beyond, are what we call surface sortie missions. Landers will come. Landers aren't shown here, but landers will come, take half the crew down, half the crew will stay behind to do maintenance and science on this orbiting station. And the way it's set up now, again, Starship will be Artemis 3, Starship will be Artemis 4, Blue Moon will be Artemis 5. Beyond that, we haven't decided yet. We'll see how these missions go, and NASA will decide what landers we want to use going forward based on their performance. Questions?
Oh yeah, we do have a question back here. Actually, while I'm walking back here, it seems like at some point there are more than one docking port. Is that how many will ultimately the final version of Artemis have docking ports?
Good question. Good question. 2 on Halo, 3 on IHAB, 5, another one on ERM and airlock, 6, 7-ish. And that's, yeah, you hit on a really challenging thing for us. I mean, the ISS is massive. It's a mansion. It's like a multi-bedroom house. This is at best a 1-bedroom condo. It's not big at all. It's very small and compact, and that's been one of our challenges with Gateway. We've got these massive, huge solar wings out there, right? We've been having so many challenges, and as we bring this, for example, that logistics module in on Artemis 4, we want to dock it at a docking port near those arrays. We use rockets to maneuver and come to dock to the station, those solar arrays act as sails. So a lot of work going in positioning the thrusters while still being able to control things, positioning the arrays so that they're at an advantageous angle so we don't break them. It's just a very compact vehicle. It makes it really challenging for us to approach and dock with the station. And then you can imagine a Starship coming in, right? I didn't put a picture of a Starship docked to this thing because it's comical. We become kind of a hood ornament for Starship, but it brings its own challenges given its enormous size. And Blue Moon is big too. Not as big as Starship, but they're both very big, massive vehicles. So those are the challenges we have with Gateway, but docking is one of them. It's not a lot of parking, to put it simply. Not a lot of parking at the Gateway.
All right, we'll go to another question here.
You mentioned it was very small. How visible, if at all, will Gateway be from Earth?
I don't know. I don't imagine it'll be all that. It's not like you'll be able to see it like you see the ISS, right? This crowd probably watches the ISS fly over every once in a while. I don't think you'll be able to see it. Maybe when Starship's there, you'll be able to catch some reflection of it off of that. I just don't know. I haven't seen any simulations as to what it would look like from here, but plus its orbit. I mean, again, it's going to be at its furthest point, 70,000 kilometers away from the moon. So you're going to have to be looking for it. So I don't know. I don't think it'll be very visible. I honestly haven't seen any simulations as well.
It's very unlikely to be a naked eye kind of a observational object. And maybe if you really got some extraordinary telescope, maybe the Vera Rubin or something might be able to pick that up, but which we'll talk about tomorrow. But anyway, I'm sorry. Go ahead, Gary.
No, that's good. That's good. That's a good question. I hadn't thought of that question before, but that's a good one. All right. So the Gateway, again, I had mentioned it earlier. It's not just a U.S. endeavor.
I apologize. Turns out I missed another question.
Oh, okay. Yeah.
Hi. I was wondering, so am I understanding correctly that SpaceX is owned mainly by Elon Musk and Blue Origin is now Jeff Bezos? So how has the economics that these billionaires entering this, things that I think used to just be NASA, right? Just our government building it. How has this impacted the space program, and how much money are they making off of our exploration and our tax dollars that could have just gone into the research?
Good question. Look, NASA has always leaned on industry to execute our missions. Certainly, Musk and Bezos have, with their vast resources, have changed the game a little bit. But I mean, I'll speak to SpaceX, right? Before I came to this project, I worked in the program here called Launch Services Program. And that's when Elon Musk started flying his Falcon system. And he put a lot of money into it for sure. But through our contracts with them and our common goals in getting their systems to succeed, they learn from us, we learn from them. We all get what we need and get where we want to go. I'll say for our particular project, which we are procuring the services to deliver logistics, I don't want to get into contract speak, but we award our contracts with a fixed price. We do it competitively. We have industry compete with each other for winning our services, the contract to provide our services. They do so with a price that they have to abide by. So we try to, we're painfully protective of the tax dollar because I pay taxes too. We all do in this office. And so we're always trying, and that's what we do. We try to make sure the money's spent correctly, that the missions succeed. And that's our role. We lean on that industry for things that we've already done. Delivering cargo has been done. NASA focuses our resources, our precious few resources, on doing things that haven't been done yet. So again, we don't have to invent how to deliver logistics. We leverage the industry in a competitive way to do that for us. So that's we get what, less than 0.5% of the budget We do a heck of a lot with what we do get, and that's how we try to do it. But certainly, billionaires, and you see it at SpaceX today. When I went to Starbase to see the money that Elon Musk is pouring into that facility, it's amazing and it's impressive. It's not your money, it's his money. And we will buy, even the HLS, the landing system, that's a commercial procurement. We'll buy that ride at a competitive price. That's why we have two landers. We have a Blue Origin, we have a SpaceX lander. Competition to keep them from charging whatever they want, which is really what NASA needs to do right now. A whole lot of our business relies on SpaceX right now. We're trying to change that. Seeing New Glenn fly from Blue Origin is awesome. Seeing the Centaur fly for ULA is awesome. We're trying to foster competitiveness so we don't get overpriced from one provider or monopoly. Is that a fair answer to your question?
Yep, thanks.
Yeah, good one. Oh, so let's talk about the international community. It's not just the U.S. endeavor. We have at the Gateway, Canadian Space Agency providing that arm. And these are barter arrangements. We don't pay money for the arm. We trade astronaut seats for robotic arm delivery kind of thing. European Space Agency, the same thing. They're providing the international habitat and that refueling module. Again, in a barter arrangement, we're not paying for those. And then the JAXA, the Japan Aerospace Agency, they're providing some systems for environmental control, the life support systems on IHAB. And we're also planning on getting a logistics module from them as well. They're flying something they call HTV-X. It's a cargo module to that station. And we're planning on getting a version of that to fly to Gateway to deliver logistics. Again, without paying for it, just from bartering typically astronaut seats for hardware. So there's another way, we expand our capability without any taxpayer dollars. We do international arrangements. And that leads me to the Artemis Accords. Again, not just the U.S. endeavor. We have this non-binding agreement across, I think it's up to 55 countries across the world. They're all listed here. I think Senegal joined us this past summer. So this is truly an international effort. This is all an agreement to set some framework for how we're going to explore our system, our solar system, Moon, Mars, and other objects for peaceful endeavors. So you can see the graphic down to the right there, all the shaded areas, how much of the world is working together for peaceful exploration of our solar system beyond Earth orbit, human exploration, and sustained exploration at that. So I think that is the end of my presentation. I really thank Drew for reaching out and having me talk about Artemis. Obviously, it's a special thing for us in NASA, and I appreciate your interest in it. Any questions? I really wish I could have been there, by the way. Last time I came up there, Drew, it was February, probably the wrong time of year to come to Binghamton. This would have been a great time to come up there. I'm sorry I couldn't be there in person.
Well, the door is always open whenever you ever make it back to visit family, or whenever you make it back for a speedy or whatever. Any other questions? Oh, we have one back here. Give me a second.
I'm particularly interested in the communications aspect of this whole process. It would appear to me that orbit that has been chosen looks like, at least in the illustration, that it will take the space station around the moon, around the backside where it would be blocked from communication with Earth. Is that true? Number one. And number two, at what point in distance does transmission delay, the time for the radio wave to reach from Earth or Moon to wherever the exploration arm happens to be, begin to impact the communications?
Yeah, we are in near constant communication. There are times where we'll pass briefly behind the moon, but it'll be so brief relative to, 6.5 day period. We're in near constant communication with Gateway and whatever's in the NRHO orbit. As far as the lag between a signal leaving Earth, getting to Gateway and coming and getting a response to it, I believe it's on the order of 2 to 3 seconds, which doesn't sound like a lot, but when you're operating a spacecraft and maybe reacting to something happening on a spacecraft, that is a long time. So one of the other big challenges with Gateway and any lunar operation, and certainly when we go further to Mars, where it'll be many, many minutes of lag, it's autonomy. These systems have to be able to autonomously react to things happening, because we may not have the time from a ground crew operator paradigm to respond quickly enough to change the outcome of a sequence of events that's happening. So autonomy is huge, and a huge test for us, again, before we go out to Mars, where there's going to be what's like a 15-minute lag when you're at Mars. Stuff has got to work on its own as best as we can design them to do so. Good question.
This is a fairly harsh radiation environment, and you get things like solar flares, solar mass injections, and it gets very much harsher very quickly. How are you going to handle that problem?
We've already launched assets in the heliocentric area out there to monitor space weather. I think we just launched some new assets to monitor that, so we get some warning of what's coming at us. The crew, part of the design of these systems is to have a safe haven for when we do detect events like that. They'll huddle in place at a position within the Gateway, for example, that offers the most protection, the most hardware between them and the incoming radiation. So that's, and then we just design into the system a lot of radiation protection, which costs us mass, which is the bane of our existence. The more massive something is, the harder it is to get up there and to where we need it. But obviously, crew is our most precious asset. So we do design into our systems radiation hardness, whether that's just enough material to protect the crew, or even in the systems, the electronic systems, protecting them from upsets from that radiation. And that's one of the things our project has had to kind of deal with. Our strategy was, again, I mentioned it several times, lean on the industry that's currently supplying the space station, lean on the heritage of those systems, not have to redevelop systems for the deep space stuff. But the ISS is within the protective, environment of the Earth, not as radiation, susceptible in a low Earth orbit as we will be up there. It's one of the first things we attack. We awarded our first contract to SpaceX, is we tell them, you gotta radiation harden your Dragon systems, and they knew that, and so they've already put millions of dollars into testing the radiation harden their systems that they have today, and it's not easy, right? Some parts are just susceptible, and then they change out a part. The new part that may not fit in the same spot on a circuit board that the old one did. Now you change the whole design of the circuit board, change the design of the circuit board, you change the whole design of the box. It just, the domino effect from there. That is one of our challenges, from protecting the crew to protecting the systems that the crew just depend on. So yeah, radiation is one of the big challenges for learning how to operate deep space. Again, we'll do it at the moon, a few days away, before we try to do it at Mars, 2 years away.
All right, let me just check the chat here again to see if
sure.
you have any other questions. Not currently, unless there's any other questions. Gary, I cannot thank you enough for your willingness to come and present just really a riveting and very, very deep presentation. I could listen to this for another 4 or 5 hours. So thanks again. Would love to have you come back again and come up and visit us. And so for those people that are here, actually, I was made aware that if you were here in this room earlier, someone found an amount of money under a chair, If you can tell me where you were sitting and how much that money was, you can have it. How's that? Is that all right?
Can I take a guess, Drew?
Yep. Where were you sitting, Gary? Okay. I'm sorry. I believe if there's some interest in the planetarium show, I think we still have educators that can offer that. Okay. Right. So Doc Carter, one of our Kopernik Astronomical Society members, will be doing a star tour with his laser in 10 minutes. So we'll call it at 10 after. We've got our scopes open. Please go and engage in them. And we have, again, a whole nother day's worth of material starting tomorrow at 9 a.m., including some solar observing. I'll actually be doing some slow scan television from the International Space Station. And also in the back against the back display case, there is a frame with a little card with Sputnik on it. And that actually, my dad was a ham radio operator, and he actually listened to Sputnik when it was launched 68 years ago tomorrow. And so he sent a note to the Russian Space Agency saying, I heard it on this, at this time, at this frequency, and they sent a card back saying, thank you for that information. And so that card is actually in the back if you want to take a look at that. So anyway, thank you all for coming again. But again, the rule here is you can't leave here until you've looked through a telescope. So get out there and check that box. Thanks again, Gary.
Thank you, everybody. Thank you, Drew.
All right. Look forward to seeing you again soon. And press on.
Yeah, come on down anytime, Drew. You're welcome to stop by.
Thanks so long.